Hello, today's lesson will be on Lewis diagrams, which is a method that we will use to show the configuration of atoms in a compound. So we will first look at ionic bonds. The ionic bond is formed by attractions between oppositely charged ions. Ionic bonds are formed between metals and nonmetals. So the metals are the majority of your periodic table. The nonmetals are all of the elements on the left-hand side, and there's a staircase that kind of pops down, and I will show you that tomorrow in class. Ionic bonds are formed by completely transferring one or more electrons. So we will begin by reviewing a Lewis dot diagram. So you would have looked at this in grades 9 and 10 science. So we're going to look at two different atoms and their ions. So we're going to start with the beryllium. Bring this in a little closer. Okay, so beryllium, first thing you need to do, is you write the symbol that we get for the chemical from the periodic table. Beryllium, we'll notice, has an ion charge of 2+, which means it has 2 electrons in its valence shell. So we'll do that, we'll denote that by putting 2 electrons around the beryllium. If there were any more, we would continue around the circle, and then we would start pairing them. But that's not the case for beryllium. Beryllium only has 2. Okay. So the beryllium ion, in its ion state, an element loses or gains its valence electrons to create a stable ion. Right. So beryllium is going to lose 2 electrons. So we're just going to write Be2+. Okay. Magnesium is kind of the same. Magnesium has the same number of valence electrons, so it's still Mg, and it has its 2 valence electrons. Okay, the magnesium ion then will be Mg2+. So our next step will be looking at drawing ionic bonds. The diagram of the ionic bonding process from neutral atoms to ions shows the valence electrons and indicating with arrows the direction in which the electrons are going. So we'll first start by drawing the Lewis dot diagram for all of the ions that are within the compound, and we'll use arrows to point to where the atoms are going. Okay, so we'll start here with sodium nitride. So sodium nitride is NNA3N. So we have 3 NAs, and your sodiums, your NAs, all have 1 valence electron. While your nitrogen, or your N, has 5 valence electrons. All right, so we'll show that all these valence electrons from the sodium go over to the nitrogen to fill up its valence shell. So to fill it up so that it has 8 total electrons in its valence shell. Okay, so what we end up with is 3 Na positives. They're positive because they've all lost an electron, which means now they have one extra proton in their nucleus, which makes them a positive ion. And we have, that goes with an N that has a full octet and happens to be 3 minus. Which gives us a final element, or final compound, Na3N. Okay, so potassium fluoride. So potassium is K, and it has 1 valence electron. Fluoride is F, and it has 7 valence electrons, which means the potassium is going to give up 1 valence electron to the fluorine. So our potassium will end up being positive, just like the nitrogen. And the fluorine will end up being negative. Which gives us a neutral atom of KF. Okay. Barium oxide. Barium has 2 valence electrons. Oxide has 6. So barium's going to give up 2 electrons to fill up the oxide. I forgot to fill in all the electrons on this fluoride over here. So 8 electrons in total around the fluorine. Okay, so from there we end up with a Ba that's 2 positive, and an O that has a full octet, and is 2 negative. Which gives us the final atom, BaO. Okay, last example, sodium oxide. So sodium is Na. It has 1 valence electron. Oxygen's O. And it has 6 valence electrons. Drew 1 too many there. Okay, if I only have 1 Na, it's only going to fill up one of those pairs. So that means I need 2 NAs to fill up oxygen totally to 8. So I end up with 2 Na positives plus 1 oxygen with its full octet. That's going to be 2 negative. And finally, we end with Na2O. A covalent bond is formed between nonmetal atoms. The nonmetals are connected by a pair or by shared pairs of electrons. A molecule is a neutral particle of 2 or more atoms bonded to each other. Covalent bonds are intramolecular forces. That is, they are inside the molecules and hold the atoms together to make the molecule. There are many types of covalent bonds. A single covalent bond is between 2 atoms with a single pair of valence electrons. Double covalent bond is when 2 atoms share 2 pairs of valence electrons. Triple covalent bond is when 2 atoms share 3 pairs of valence electrons. Multiple bonds are shorter and stronger than their corresponding single bond counterparts. Lewis theory. Gilbert, Newton, and Lewis focuses on the valence electrons. Since the outermost electrons are the ones with the highest energy and furthest from the nucleus, and are therefore the ones most exposed to other atoms when bonds form. Unpaired electrons represent places where electrons can be gained in ionic compounds, or electrons can be shared to form molar or covalent compounds. The valence electrons of helium are better represented by 2 dot pairs, since in all the noble gases, the valence electrons are in filled shells and not available for bonding. The shared electron in a covalent bond act like they belong to both atoms in the bond, and they bond the 2 atoms together into a molecule. The shared electrons are usually represented by a line between the bonded atoms. The pairs of electrons that are bonded and the unshared pairs of electrons are lone pairs or non-bonding pairs. Their structure, I think that was supposed to go back up in the top line. It's almost done. To write the Lewis structure for a molecule, first you need to count the number of valence electrons in the molecule or polyatomic ion. For example, in H2O, it has 2 electrons, or 1 electron for each H, plus the 6 from the oxygen, so 8 valence electrons. Cl4 has 4 in the carbon, and 4 times 7 from the chlorine, so therefore it has 32 valence electrons. For anions, add 1 valence electron for each unit of negative charge. For cations, subtract 1 electron for each unit of positive charge. For example, NO3 is 5 plus 3 times 6 from the oxygen plus 1, which is 24, because the NO3 is negative. NO4 plus, or NH4 plus, has 5 from the nitrogen, 4 times 1 from the hydrogen, and minus 1 for the charge, which gives us 8 valence electrons. Then we're going to place the atoms relative to each other. For any molecule in the form AXN, place the atom with the lower number in the center. If A and X are in the same group, place the atom with the higher period number in the center. This places the least electronegative atom in the center. H is never, under any circumstances, a central atom. Draw a single bond from each terminal arm to each connected atom. Each bond uses 2 valence electrons. Distribute the remaining valence electrons in pairs so that each atom obtains 8 electrons, or 2 for hydrogen. Place the lone pairs on the terminal atoms first, and place any remaining valence electrons on the central atom. The number of electrons in the final structure must equal the number of valence electrons from step 1. If an atom still does not have an octet, move a lone pair from an adjacent atom in between the 2 atoms and make a double or a triple bond. So CH4 will be the first example we look at. I've done the math already, and in CH4 we should have 8 valence electrons. There's 4 electrons in the carbon and 1 electron in each of the 4 hydrogens. So that gives us a total of 8. So we're going to start, and we're going to place the carbon in the center and the 4 H's all around. Then we'll bond all of the atoms together. We'll then count and see if we have enough electrons. So each bond is 2 electrons. So we have 4 bonds. Therefore, we have 8 electrons. So this uses up all of the valence electrons, and the octet rule is satisfied everywhere. And all of the atoms have a formal charge of 0. All right, NH3 is going to be the second atom that we look at. So the charge for N is 5. Again, the charge for H is 1, and there's 3 of those. So 5 plus 3 times 1 gives us 8 valence electrons. So we're going to start by placing the N, the nitrogen, in the center, and the H's all around. So there's 3 H's. We'll then bond all those together and count and see how many valence electrons we have. There's 3 bonds, which means we only have 6 electrons. So the last 2 electrons can't go on the H's because, remember, hydrogen can only have 2 valence electrons. And with the bond, now it's sharing valence electrons with the nitrogen, so it's full. It can't take any more electrons. That means we need to put the last 2 electrons on the nitrogen, just like that. Our last example is of H3O positive. So we have 8 valence electrons again. So in these 8 electrons, we get 3 from each one from each of the 3 hydrogens, 6 from the oxygen, and then we subtract 1 because the atom that we're looking at is positive, which means it has more protons than electrons, so it must be short 1 electron. So we're going to place the O in the center, as always. 3 H's that are bonded to that O. So now I only have 6 electrons around the O, which means I need to put 2 more electrons on the O, so its octet rule is satisfied. All right, that's the end of the lesson. If you have any questions, we can talk tomorrow in class. See you then.